Good morning, everyone. Today we're going to look at Module 26. Talks about evaluating alerts. So we begin. Let's look at the module objectives. The module title is Evaluating Alerts. Module objective. This is to explain the process of evaluating alerts. So looking at the table, we have the topic title, topic objective. So the first we're going to look at is the source of alerts, which is to identify the structure of alerts, followed by overview of alert evaluation, which is to explain how alerts are classified. So we'll start with the first one, sources of alerts. Okay. So in this, we're trying to evaluate the alert by using a security suite or an open source suite called the security onion. So what's the security onion? The security onion is an open source suite of network security monitoring NSM tools that run on an Ubuntu Linux distribution. We've talked about the Linux in one of our modules and the types of distros they have. That's another short for distribution. So security onion tools provide three core functions for the cybersecurity analyst, such as full packet capture and data types, network-based and host-based intrusion detection systems, and alert analyst tools. So there are a lot of tools you find within the security onion that are integrated, okay? So security onion can be installed as a standalone installation or as a sensor and server platform. So these are the options provided for you to install the security onion, which means it can be on a single PC, or it can be a sensor which can be resided within a router or a switch, and it can be on a server platform. So some components of security onion are owned and maintained by corporations such as Cisco and Riverbend Technologies, but are made available as open source. So it means that some of this component is not everything basically owned by a single company. So these various components are being produced or owned by different companies, but they are integrated into one where we have this security onion. Detection tools for collecting alerts. Security onion contains many components. It is an integrated environment which is designed to simplify the deployment of a comprehensive NSM solution. So what it means is that we have this integration of various components that makes one as a security onion. So showing the diagram you see is a figure to illustrate the way in which components of the security onion work together. So this component, you can see them, they are divided into three categories. You have the analysis, we have the detection, and the data. All these form what we call the security onion architecture. So looking at the analysis, we have this Squeal, Wireshark, Kibana. Then the detection, we have CAPME, Snot, Zigbro, OSEC, Wazoo, Sorikata. And finally, the data, we have the PCAPs, content data, transaction data, session data, host logs, alert data, syslog data, metadata. Now, looking at the detection tools for collecting alerts, which continues, the following table lists the detection tools of security onion. Looking at the first component, under one of the detection tools, we have the CAPME. We have the CAPME. This is a web application that allows viewing of PCAP transcripts, render with the TCP flow or Zik tools. It is a web application that allows viewing of pickup transcript rendered with TCP or Zik tools, CAPMI, and can be accessed from the enterprise log search and archive ELSA tools. So CAPMI provides the cybersecurity analyst with the easy to read means of viewing an entire layer 4 session. So CAPMI acts as a plugin to ELSA and provide access to relevant pickup files that can be opened in Wireshark. Okay, so that's it for this. So let's look at the next one, which is the SNOT. This is a network intrusion detection system, NIDS. Okay, it is important source of alerts data that is indexed in SQL analysis tool. SNOT uses rules and signatures to generate alerts. So SNOT can automatically download new rules using the pulled POC component of Security Onion. SNOT and pull POC are open source tools that are sponsored by who? Cisco. Okay. So it means to update these particular files, it means there's a way using the pull POC, the download can be made automatically, which helps SNOT to function. Okay. So the next one is Zik. Okay, which was formerly known as Brew. This is a NIDS that uses more of the behavior-based approach to intrusion detection. Rather than using signature rules, the Zik uses policies, okay? Policies in the form of script that determine what data to log and when to issue alert notification. Zik can also submit file attachment for malware analysis, block access to malicious location, and shut down a computer that appears to be violating security policies. So you should note that some interfaces within Security Onion have yet to be updated with a brew to Zik name change. Okay. Let's look at the next one, which is the OSSEC. Okay, OSSEC, this is a host-based intrusion detection system, HIDS, that is integrated into Security Onion. It is actively monitors host system operations, including conducting file integrity monitoring, local log monitoring, system process monitoring, and rootkit detection. OSSEC alerts and log data are available to Squirrel and Kibana. So OSSEC requires an agent to be running on the Windows computers in the enterprise. The next one is Wazoo. Wazoo. It is a full-feature solution that provides a broad spectrum of endpoint protection mechanism, including host log file analysis, file integrity monitoring, vulnerability detection, configuration assessment, and incident response. Okay, so it means like OSSEC, it requires agent to be running on network hosts. So these ones are basically, this particular one is basically a host-based kind of intrusion whereby you have a network or which you have an agent that runs on that host. Okay. The next one is the Suricata. Suricata, this is a NIDS that uses a signature-based approach. It can also be used for inline intrusion prevention. It is similar to Zik. However, Suricata uses native multi-threading, which allows the distribution of packet stream processing across multiple processor cores. It also includes some additional features such as reputation-based blocking and support for graphic processing unit, GPU, multi-threading for performance improvement. Okay, so that's what you get with sorry, kata. Let's go to the next line or the next slide. So in the next slide, we have analysis tools. Security Onion integrate these various types of data and intrusion detection system, IDS logs into a single platform through the following tools. So the intrusion detection system is able to generate or gather these logs with the help of these following tools, which are Squill, Kibana, Wireshark, and Zig. So let's look at the first one, which is a Squill. This provides a high-level console for investigating security alerts from a wide variety of sources. So sources can be what those sensors that I've mentioned earlier. So Squill serves as a starting point in the investigation of security alerts. Many data sources are available by pivoting directly from Squill to other tools. It means you should be able to gain access to the information of Squill from other tools that you use. So it is an interactive. So now looking at Kibana. Kibana, it's an interactive dashboard interface to Elasticsearch data. It allows querying of NSN data and provides flexible visualizations of that data. It is possible to pivot from Squill directly into Kibana to see contextualized displays. So you have a dashboard with a user interface that makes it easy to analyze the logs or the data. So Wireshark, it is a packet capture application that is integrated into the Security Onion suite. It can be opened directly from other tools and display full packet capture relevant to an analysis. We've talked about this in the previous one of the modules. Okay, so let's go down to Zik. What is Zik? This is a network traffic analyzer that serves as a security monitor. It inspects all traffic on a network segment and enables in-depth analysis of that data. So pivoting from Squill into Zik provide access to very accurate transaction logs, file content, and customized output. So these are some of these analysis tools. It doesn't mean that you have to stick to one. You can combine all these tools with the aim of investigating or with the aim of analyzing. So let's look at alert generation. Security alert are notification messages that are generated by NSM tools, systems, and security devices. Alert can come in many forms depending on the source. So in Security Onion, Squill provides a console that integrates alert from multiple sources into a time-stamped queue. So a cybersecurity analyst walk through the security queue, investigating, classifying, escalating, or retiring alerts. Alert will generally include 5 tuples, information as well as timestamps and information identifying which device or system generated the alert. So these 5 tuples are key in your investigation, where the first one, SRC IP, talks about the source IP address for the event. The S port talks about the source local layer 4 port for the event. Then the DST IP, which talks about the destination IP for the event. The D port is all about the destination layer 4 port for the event. And finally, the PR, the IP protocol number for the event. So these are key in terms of security alert. These are areas you can also you need to look at. So additional information can be whether a permit or denied decisions was applied to the traffic, some capture data from the packet payload, or a hash value for a downloaded file, or any of a variety of data. Okay. So we'll look at the figure that talks more on the Squill application window. So looking at the diagram where you have the Squill window, the Squill window, the figure shows this scroll application window with the queue of alerts that are waiting to be investigated in the top portion of the interface. The fields available for the real-time event are as follows. So what do we mean by ST? So ST means what? Status. So this is the status of the event. The event is color coded by priority based on the category of alert. There are 4 priority levels: very low, low, medium, and high. And the color range from light yellow to red as the priority increases. So it means when you have a light yellow, it means less attention is needed. When it grows up to the red, it means more a high attention is needed in looking at the issue. So CNT, this is the count for the number of times this event has been detected for the same source and destination IP address. The system has determined that this set of event is correlated. So what we mean here is that you can have a particular event that occur multiple times, and instead of giving or separating the timestamps, or I mean the event that occur multiple times, you separate it, you rather will put them as a single one because it happens multiple times. For instance, when you have uh, attempt on password, which was done or it happened 5 times, the whole thing is being recorded as 1. And the count also will also be added to it, as since it is 5 times, you will now have 5. So what I mean as 1, it's you're going to have a single line of 1 of this count, but that's the 1 of the rule. But in terms of the number of times it happens, you can see it will be given as 5. So assuming the person attempted to log into the account 5 times, that's the failed at times. 5 times, that will be recorded. So sensor, this is the agent reporting the event. The available sensors and the identifying numbers can be found in the agent status tab of the pane, which appears below the event window on the left. So what did generate the information is what we are talking of. So it could be a router, it could be a switch that was designed to generate designed to act as a sensor, or it could be an IDS or IPS that did that. So in this case, our sensor from the diagram shows security onion. Then we have another one called the alert ID. The alert ID. So these two part number represent the sensor that has reported the problem and the event number for that sensor. We can see from the figure that the largest number of events that are displayed are from OSEC sensor 1, okay? The OSEC sensor has reported 8 sets of correlated events. Of this event, 232 have been reported with the ID 1.24, okay? So let's go down to date time. This is a timestamp for the event. In the case of correlated event, it is timestamp for the first event. Then event message. This is the identifying text for the event. This is configured in the rule that triggered the alert. The associated rule can be viewed in the right-hand pane just above the packet data. To display the rule, the show rule checkbox must be selected, which is here, okay, where you can see my cursor. So that is key when you want to do that. Okay, so let's look at rules and alerts. Alert can come from a number of sources, okay, just like we've mentioned earlier. So let's look at some of these sources. The NIDS, And with the help of NIDS, what can you use in the security onion suite to investigate or to analyze is what we've mentioned it earlier, the snort zig and the suricata. HIDS, we have the OSEC wazoo. Then asset management. Asset management and monitoring, we have the passive asset detection system, PADS. Then the HTTP, DNS, and TCP transaction is recorded by ZIG and PCAPs. Then syslog messages, you have multiple sources. The information found in the alerts that are displayed in school will differ in message format because they come from different sources. The school alert in the figure was triggered by a rule that was configured in Snort. Okay. So it is important for the cybersecurity analysts to be able to interpret what triggered the alert so that the alert can be investigated. For this reason, the cybersecurity analyst should understand the component of snort rules, which are a major source of alert in security onion. Okay. So the next one, want to look at the snort rule structure, how the structure is. So let's start. Snort rule consists of two sections as shown in the figure, the rule header and the rule options. The rule location is sometimes added by SQL. Okay. So what do you have? You can see the message, alert IP, any, hyphen, greater sign, any, then the message, and so on. So let's go down to the next table where you have component example explanation. So what each of these structure mean. So we have the rule header. The rule header is where you have the alert IP, any, hyphen, greater, any, okay? So this contain the action to be taken, source and destination address, and port and the direction of traffic flow. Then we have another rule option, which is the message, GPL attack response ID check returned route. This includes the message to be displayed, details of packet content, alert type, source ID, and additional details, such as a reference for the rule or vulnerability. So that's what you have within this particular rule. Then how about the location of this rule? It's the location of this rule is within a file. Okay, so the file name is downloaded.rules. So if you want to have a location of that file, you go to NSM server underscore data security onion. That is where the rule is kept. Rules that's sec onion hyphen ethernet 1 -1, then downloaded.rules. So within that file, under the line 692, that is where this is captured. That is where the rule is captured. So the rule header contains the action, protocols, addressing, and port information as shown in the figure. The structure of the header portion is consistent between snort alert rule. Snort can be configured to use variables to represent internal and external IP addresses. So looking at this, you have alert IP, then you have any hyphen, greater sign, any, then the message up to. This is just a repeat of what we have in the previous slide. So component explanation. So when you have an alert, this alert, that's when it is written alert in the message. What it means is the action to be taken is to issue an alert. Other actions are log and pass. So it means it's not only alert you may see. In some cases, you see log and pass. So IP, this is the protocol. Then the specified source is any IP address and any layer 4 port. Then the hyphen and the greater sign means what? The direction of flow is from the source to the destination. Then the specified destination is any IP address and any layer 4 port. So you can see the 5 tuple has been captured here. You're able to get what the source IP address, the source layer 4 port, then the destination IP address, then the destination layer 4 port, and finally the protocol. So you can see these are key things that you always find in this SNOT rule structure. The rule options. So the rule options, the structure of the options section of the rule is variable. It is the portion of the rule that is enclosed in parentheses. Okay, let's look at it. Parentheses, as you can see from the message, okay, as shown in the figure. It contains a text message that identifies the alert. It also contains metadata about the alert, such as the URL, the Uniform Resource Locator. So SNOT rule messages may include the source of the rule. 3 common sources for SNOT rules are what? The GPL. We're talking about the sources for the SNOT rules. Okay, the GPL, older SNOT rules that were created by SourceFire and distributed under a GPL version 2. The GPL rule set is not Cisco Talos certified. The GPL rule set can be downloaded from the SNOT website, and it is included in the security onion. You know, when we talked about downloading using the pull POC, so you can download the rules and integrate it into, included into the security onion. Then the ET, SNOT rules from emerging threat, which is a collection of points for SNOT rules from multiple sources. The ET rule set contains rules from multiple categories. A set of ET rules is included with security onion. Emerging threat is a division of proof point, Inc. Then we now have the VRT. These rules are immediately available to subscribers, and that's paid for, and are released to registered user 30 days after they were created, with some limitations. They are now created and maintained by Cisco Talos. So rules can be downloaded automatically from snot.org using the POC rule management utility that is included with Security Onion. So alerts that are not generated by SNOT rules are identified by OSEC or PATAX, among others. In addition, custom local rules can be created, okay? So you can create your own custom, or you get the ones from those places from the snot.org website, and you pull them down into your security onion, okay? So let's look at the other components. The message MSG, text that describes the alert. As you can see from the message, you have GPL attack, response ID, check return route, okay? Then content refers to the content of the packet. In this case, an alert will be sent if the literal text UID equals to 0 root appears anywhere in the packet data. Value specifying the location of the text can be provided. Just as you can see, we have UID equals to 0. Then you have 28 root 29 and so on, okay? So that's what you get within this. So reference, this is not shown in the figure. It is often a link to a URL maybe to a site that provides more information on the rule. In this case, the SID is a hyperlink is a hyperlink to the source of the rule on the internet. So class type, a category for the attack. Snort includes a set of default categories that have one of 4 priority values. Then SID, you have a unique numeric identifier for the rule. Then rev, the revision of the rule that is represented by the SID. So we're going to look at the lab, where it will give us a better and clearer understanding on what we have discussed in our slides so far. So in the lab, we're going to look at the snort and firewall rules, where you complete the following objectives: perform live monitoring of IDS and event, configure your own customized firewall rules to stop internal hosts from contacting a malware hosting server, craft a malicious packet and launch it against an internal target, create a customized IDS rule to detect the customized attack and issue an alert based on it. Okay. So overview of alert evaluation. The need for alert evaluation. The threat landscape is constantly changing as new vulnerabilities and threats are discovered. As user and organizational needs change, so also does the attack surface would change. So threat actors have learned how to quickly vary features of their exploit in order to evade detection. Okay, people are coming up with different methods in which sensors will not be able to detect them. They use some form of stealth method in which they can infiltrate structures or system. It is better to have alerts that are sometimes generated by innocent traffic, that is to have rules that miss malicious traffic. So it is necessary to have skilled cybersecurity analysts investigate alerts to determine if an exploit has actually occurred. So what it means is sometimes these rules might not detect the incoming problem because of the level at which the attacker is able to improve on his message or code. So it's now left for you as the analyst to also do further investigation onto that alert. So tier 1 cybersecurity analysts will walk through queues of alert in a tool like Squirrel, pivoting to tools like Zik, Wireshark, and Kibana to verify that an alert represents an actual exploit. So it means even the system can even give a wrong information or a right information about an alert. So it's left for you to do further investigation, okay, as an analyst. So evaluating. Evaluating alert. Security incidents are classified using a scheme borrowed from medical diagnosis. This classification scheme is used to guide actions and to evaluate diagnostic procedures, okay? For example, when a patient visits a doctor for a routine examination, one of the doctor's tasks is to determine whether the patient is sick. One of the outcomes can be a correct determination that disease is present and the patient is sick. Another outcome can be that there is no disease and the patient is healthy. So these are the common scenario you may get also when making your the investigation. The concern is that either diagnosis can be accurate or true, or inaccurate or false. For example, the doctor could miss the signs of disease and make the incorrect determination that the patient is well when they are in fact sick. Another possible error is to rule that a patient is sick when that patient is in fact healthy. False diagnoses are either costly or dangerous. Okay, so in network security analysis, the cybersecurity analyst is presented with an alert. This is similar to a patient going to the doctor and saying, I am sick. The cybersecurity analyst, like the doctor, needs to determine if the diagnosis is true. The cybersecurity analyst asks, the system says that an exploit has occurred. Is this true? So that's the question you have. So let's look at the alerts and how they are classified. So they are classified as follows. So where you have true positive, the alert has been verified to be an actual security incident. Then when you have false positive, the alert does not indicate an actual security incident. Benign activity that result in the false positive is sometimes referred to as benign trigger. Then alternative situation is that an alert was not generated. The absence of an alert can be classified as true negative. So no security incident has occurred. The activity is benign. So false negative, an undetected incident has occurred. So you can see a table to give you a summary of the whole thing. So when an alert is issued, it will receive one of the 4 possible classification. Incident occur, no incident occur. That's when you look at under the positive alerts. So under the positive alert, when we say incident occur, so it is true. When no incident is occurred, it is false. So under the negative or no alert exists. So if it is true, you have no incident occur. If it is false, you have incident occur. So true positives are the desired type of alert. They mean that the rules that generated the alert have worked correctly. So the rule that you have that generated is working effectively. So false positives are not desirable. So although they do not indicate that an undetected exploit has occurred, they are costly because cybersecurity analysts must investigate false alarm. So true negatives are desirable. They indicate that the burning normal traffic is correctly ignored and erroneous alerts are not being issued. So false negative are dangerous. They indicate that exploits are not being detected by the security system that are in place. So note, true events are desirable, false events are undesirable and potentially dangerous. Okay. So burning events are those that should not trigger alerts. Excess burning events indicate that some rules or other detectors need to be improved or eliminated. So when a true positive are suspected, a cybersecurity analyst is required to escalate the alert to a higher level for investigation. The investigator will move forward with the investigation in order to confirm the incident and identify any potential damage that may have been caused. So a cybersecurity analyst may also be responsible for informing security personnel that false positives are occurring to the extent that the cybersecurity analyst time is seriously impacted. False negative may be discovered well after an exploit has occurred. This can happen through retrospective security analysis. RSA can occur when a newly obtained rules or other threat intelligence is applied to archive network security data. For this reason, it is important to monitor threat intelligence to learn of new vulnerabilities and exploits and to evaluate likelihood that the network was vulnerable to them at some time in the past. Okay. So let's look at deterministic analysis and probabilistic analysis. Deterministic analysis evaluates risks based on what is known about a vulnerability. This type of risk analysis can only describe the worst case. Okay. So, however, many threat actors, although aware of the process to carry out an exploit, may lack the knowledge or expertise to successfully complete each step on the path to the successful exploit. This can give the cybersecurity analyst an opportunity to detect the exploit and stop it before it proceeds any further. So that's probabilistic analysis, estimate the potential sources of an exploit by estimating the likelihood that if one step in an exploit has successfully been completed, that the next step will also be successful. So probabilistic analysis is especially useful in real-time network security analysis, in which numerous variables are at play, and a given threat actor can make unknown decision as an exploit is persuade. Okay. So in the deterministic analysis, all information to accomplish an exploit is assumed to be known. The probabilistic analysis, it is assumed that the port numbers that will be used can only be predicted with some degree of confidence. So the two approaches are summarized below. Okay. Okay. So deterministic analysis for an exploit to be successful, all prior steps in the exploit must also be successful. Okay. So the cybersecurity analyst knows the step for a successful exploit. So probabilistic analysis, statistical techniques are used to determine the probability that a successful exploit will occur based on the likelihood that each step in the exploit will succeed. Okay. So we have come to the end of evaluating the alerts, and this is what we've done so far based on the question, what did I learn in this module? So what we learn in this module, this Security Onion is an open source suite of network security monitoring NSM tools that run on an Ubuntu Linux distribution. So Security Onion tools provide 3 core functions for the cybersecurity analyst: full packet capture and data types, network-based and host-based intrusion detection systems, and alert analyst tools. Security Onion integrates the data and IDS logs into a single platform through the following tools. So Swill serves as a starting point in the investigation of security alert. Kibana, it's an interactive dashboard interface to Elasticsearch data. The Wireshark packet capture application is integrated into the Security Onion suite. Then Zik is a network traffic analyzer that serves as a security monitor. Then Snort, in a network intrusion detection system, NIDS, is an important source of alert that is indexed in school analysis tool. Alerts can be classified as true positive. The alert has been verified to be an actual security incident, or false positive. The alert does not indicate an actual security incident. Then an alternative situation is that an alert was not generated. The absence of an alert can be classified as true negative, no security incident has occurred, the activity is benign, and false negative, an undetected incident has occurred. So deterministic analysis evaluates risks based on what is known about a vulnerability. Then probabilistic analysis estimates the potential sources of an exploit by estimating the likelihood that if one step is in an exploit has successfully been completed, that the next step will also be successful. So thank you very much for having your time to share with what we have today. I hope that we meet next time to continue with the next module, which is on working with network security data. So thank you very much and have a nice day. Bye-bye.